बस वीडियो रिकॉर्डिंग हो जाता है. Okay, so what we have learned about the 5 selections in the last class. With the example of oxygen molecule, we try to understand we, uh, two examples we have discussed, plus and then oxygen molecules to understand how we assign the terms in it, right? So now you can do it on your own. With this, so now you understand all these things. The parity. So three selections for a unit system. Two selections for symmetry. And then yeah, charge. No. Charge means that is symmetry. Symmetry is the that plus minus is your the of one versus and the reflection symmetry. Reflection symmetry applies to sigma. In the sigma term, then only you will look for that plus minus superscript on the right hand side. In all other cases, you don't have to worry about that. So it applies in case of oxygen, it does apply, and all these things we discussed earlier. And G means gerate, symmetric. That is, if mathematically you have to treat it as a function, it will be even function, just as behavior of plus one. Ungerate, antisymmetric behavior is like minus one, arithmetic sense, and and so total any closed shell dynamic molecule will have this homonuclear dynamic molecule will have this kind of this symbol, this term symbol. Ground state of any homonuclear dynamic molecule will be this term symbol for closed shell homonuclear dielectric molecule, where spin is zero. Okay, so whenever you have pi electrons, you will have plus minus lambda plus minus 1. तो ये सब चीजें हमने कल तक की क्लास में सीखा है, ठीक है? And now, so we assigned oxygen its term symbol based on these considerations, and so 3 sigma, and then you assign this G parity of this particular. So G1. So you understand how we are doing this? हमने कैसे किया था? V एक एक इलेक्ट्रॉन के लिए ये जिस ऑर्बिटल में है, ये किस ऑर्बिटल में है, G, and closed shell this thing, whole thing. ठीक है? So looking at all these things, we assigned overall parity. Reflection with respect to this ठीक है, तो इसमें भी प्लस प्लस माइन बेसिक फंडा वही है. अगर दो इलेक्ट्रॉन होंगे तो इस तरह से आपको कंबाइन करना है. इफ यू हैव 2 electrons, then look at each of these orbitals, how they behave under reflection operation, and then assign this plus minus, and then together how they you will place this will be the behavior. Minus minus will be plus, plus plus will be plus. Okay, so reflection only applies to Z again and again. We have referring to it. No reflection labels for lambda greater than 0. So these were the basic rules that we learned, and vertical, horizontal orbital, you look for a mirror plane either in the plane of the board or in the perpendicular to the board, and you will arrive at the conclusion that this is having plus, this is minus. Or if we choose this plane of the board as the mirror plane, if you however choose to be different, देखिए दोनों स्लाइड में दोनों एग्जांपल दिया है, एक में इन्होंने बोर्ड को कंसीडर किया गया है, एक में इसको कंसीडर किया गया। ठीक है, लेबल्स आप देख सकते हैं कैसे वो जो, हाँ, जो हॉरिजॉन्टल वाला था वो उसका लेबल इसमें प्लस हो जा रहा है, इसमें माइनस, लेकिन प्लस और माइनस एक में प्लस एक माइनस है। ठीक है, that is easy to understand. So, and then we arrived at this thing, properties of O2 in lower oxidation state. This is the ground state, triplet. Ground state is triplet, and excited state is, there are two singlet states which are next to it in terms of energy, first, second. So एक में उसी ऑर्बिटल में जहाँ है वहाँ पे फ्लिप कर गया, तो ये वाला इलेक्ट्रॉन है इट फ्लिप्स, फ्लिप कर दो तो वो, ये तीसरी वाली सिचुएशन, इफ यू फ्लिप द स्पिन, उसी ऑर्बिटल दो पाई पाई स्टार ऑर्बिटल में कोई इलेक्ट्रॉन है पहले फ्लिप वाला, दैट इज द सिचुएशन। और वो जो 2 0 देख लो, एक में ही दोनों आ गया, फ्लिप किया और इसमें, so the, so if you analyze in a very, you can get all the fundamentals, the ground state. So oxygen atom 1 in the ground state, oxygen atom 2 in the ground state at infinite distance, when they come together the energy drops and you have a potential well which is formed, similar to what we did for hydrogen molecule in the first semester. And then you can get all these states if you consider gradually changing one of the atoms, state of the atom, and then construction of the molecule. So, and finally, this is what is expected from you, O2, O2 minus, O2 minus, and you should be able to write these term symbols in your notebooks. ठीक है, मंडे तक सबका होना चाहिए। ठीक है, उसको डिटेल में आपका सब ड्रॉ दिस डेमो डायग्राम, तुम भी कॉपी भी करो, तुम्हारा ही नोट्स अच्छा बनेगा ना, करोगे तो ना। दिस इज एक्सपेक्टेड, 3 दिन से बोल रहा हूँ कोई नहीं कर रहा, आज टुडे इज थर्ड डे। लिख लो कि तुमको टर्म सिंबल लिखना है, अपनी कॉपी में लिखो, N2 N2 प्लस N2 माइनस लिखो, सुपर ऑक्साइड पर ऑक्साइड O2 का तो दिया हुआ है, O2 प्लस का 3 जो करके लाएगा उसको 5 नंबर मिलेगा। असाइनमेंट, एक असाइनमेंट ऐसा भी हो सकता है, आपको उसी दिन कॉपी जिसने किया है जमा कर दे, उस लिस्ट में 5-5 नंबर, फिर अगले दिन आपको कुछ और करेंगे, अगले दिन कॉपी में 5 नंबर और आपको मिल जाएगा, 10 नंबर का टेस्ट हो गया। ठीक, कीजिए, मंडे तक अच्छे से कर लीजिए, अपनी कॉपी में बनाइए, स्नैपशॉट बना करके भी आप अपलोड कर सकते हैं, उससे बस 7 8 8 मॉड्यूल्स टोटल 8 इसमें मैं एक O2 का तो ऑलरेडी है, O2 प्लस कर, O2 प्लस कर सबका टर्म्स की वैल्यू निकालना है, प्रैक्टिस एमओटी तो एक का भी बनाओगे तो बाकी सब आप, you should be able to write the molecular configuration, electronic configuration of the molecule based on that, तो एक एमओटी से बना के सारा कर सकते हैं, but at least do something, आप कुछ कर नहीं रहे हो, ठीक है, नहीं तो एकदम से नहीं कर पाओगे, और ऐसे प्रैक्टिस करोगे तो तुम्हारे दिमाग में क्लियर होता रहेगा। एग्जाम के टाइम में एक बार में जब सब पढ़ोगे ना तो कुछ नहीं आएगा, क्लॉग योर माइंड. दिस इज अ टाइम टू ओपन अप, अपने दिमाग खोलो. नहीं तो जब एकदम से सब कुछ पड़ जाएगा दिमाग में, सब बंद हो जाएगा, कुछ नहीं. इस तरह से ग्रैब करो, मतलब वो करोगे एंड देन वो में टू द नेक्स्ट डे, वो वाला सिचुएशन नहीं. सो ये सब हमने किया. सो लास्ट क्लास में, सो यू हैव टू लुक फॉर कंजर्वेशन ऑफ फोटॉन्स एंगुलर मोमेंटम. यही आपका मेन है, उसी से सारा सिलेक्शन रूल आता है. एंड दीज वर द चेंजेस फॉर द चेंज इन एंगुलर मोमेंटम. वी हैव थ्री रूल्स, 1, 2, 3. Capital lambda is for the total orbital angular momentum and total spin angular momentum, and this is the total angular momentum. तीन अलग अलग तरह से बताया था. और ये this is only the component along the internuclear axis is to be conserved. बस. फिर उसके बाद two selection rules for the change in symmetry, concerning the change in symmetry during the transition. So what kind of, it turns out that only these two transitions are allowed for sigma. If the term symbol is sigma, and the other one you very well know, and we have already discussed in the last class. Nothing. So G to U and U to G, that odd even function consideration. So that way it was clear. So if somehow the symmetry is broken, so it is important that this will happen for the center of symmetry of the molecule, vibronic transitions. So if it is vibrating molecule, DD transition is a GG transition. So remember this thing, and that's why it is called. So vibrating molecule, the symmetry is broken, and then G to G or U to U transition is possible. Okay. So it turns out that Laporte selection rule only that so it is the consideration of initial, final, and this wave function, and it will be valid only if both the functions. So I told you that the dipole moment operator is the odd function. If you are looking at this, and so these two must be, the combination of the other two must also be odd. Okay, only then it will work out to be overall having some finite value. So transition dipole will be created, and that will interact with the oscillating electric field. ठीक है. So three components x, y and z all are ungeared with respect to center of symmetry. With respect to center of symmetry, x, y, z तीनों ungeared, u की तरह behave करेंगे. ठीक है. And four, so this kind of transition only G to G, G to G or U to U transition is not allowed. So the two cases are discussed over here, U, U, U. दोनों केस डिस्कस किया हुआ है, देख रहे हैं. When we are looking for the other consideration, symmetry consideration, that is plus and minus with respect to the deflection operation, then overall symmetry. So this relates to the component of Z. Z component, only the Z component of dipole moment is effective, and Z component is the along internuclear axis. तो कोई भी प्लेन लो फ्रंट, ये रिफ्लेक्शन मिरर ऑपरेशन में ये वाला या ये वाला, Z पे कोई असर नहीं करता. It behaves as an even function under this set of thing, and in that case, so that will behave as a even function. So if this is even, this is the Z component, of dipole moment under reflection. रिफ्लेक्शन ऑपरेशन जब आप करोगे उसका कंसीडरेशन करोगे उसमें कोई चेंज नहीं आएगा so that will remain behave as even function so plus minus if you put it like this plus one of the functions is plus sign and another one has minus sign with respect to the reflection symmetry then overall is minus and the overall integral will be 0 odd function any odd function integral becomes 0 even function ये जो यहाँ पे मैं लिखा था this has to be a even even function अगर ये तीन चीजों का combination है the combination of three things if it is odd then still it becomes 0 you have finite quantity which is even so overall becomes something that so यहाँ पे if you place this then it is not allowed so minus to minus or plus to plus will be allowed and then a simple question was asked that out of this which one is allowed and if you look carefully only this one is valid all others are not allowed which would be violated यहाँ पे देखिए क्यों नहीं होगा और लास्ट वाला क्यों होगा why is allowed and why other four are not allowed you should be able to answer based on the discussion that we had in the last two classes उसके basis पे आप ये कर सकते हैं ठीक है and so now we are going to look into the finer details of the electronic spectra as we have when we were discussing vibration spectra we saw rotational fine structures because some of the rotational excitation was also random and here in this case we will be having when this ground state is excited with electricity each so there is a specific vibration that will be excited there might be excitation of the electricity from 0 to 1 so in a well resolved spectrum we can have this kind of spikes representing that vibrational transition occurring along with the electron transition. So then accompanying vibrational transition is seen as spikes on the top of this overall spectrum. So that is your vibrational fine structure. Vibrational structure in electronic spectrum. So the spectrum that you are seeing here is that one typical example that is given is ultraviolet. This is UV range, nanometer में है 250 nanometer sulfur peroxide at 298 Kelvin. So in a gas phase, you can get these fine structures very well resolved. So these sharp lines correspond to the transition, the spikes that you see for the different vibrational levels, starting from the ground electronic state, ground vibration before the excited electronic state to a different vibration. So that is seen here as and to understand this we have to take into account there is a principle called Frank quantum principle. Frank quantum principle and that is applied while explaining this structure, the fine structures. So what it tells in Frank quantum principle is that the molecule is vibrating at the same time photons comes, the photon comes and it is absorbed. Okay? So but the time scale of vibration and the time scale of electronic excitation that will be different. The time scale of vibration is around 2 seconds, whereas time scale for electronic excitation is around 2 seconds. 10 to the power minus 15, 10 to the power minus 12. So 1000 times. So, so what it says जो लिखा है उसका मतलब यही है कि practically जब इलेक्ट्रॉन एक्साइट हो रहा है the nuclei are मतलब वो इतना फास्ट प्रोसेस है 1000 टाइम फास्ट कर रहा है तो इसको at that particular instant when the proton is absorbed the electron goes to this excited state the nuclear positions are not changed nuclei are the same but because the excitation has occurred the figure of the is of the bond बर्तन में ब्रेक है और ब्रेक का प्रोफाइल चेंज है ठीक है तो दैट मींस वी हैव इलेक्ट्रॉन डेंसिटी अराउंड न्यूक्लियर एक्सचेंज एंड थोड़ी देर के बाद वो एडजस्ट करेगा वी स्टार्ट वी एडजस्टिंग एंड देन सिचुएशन ये अगले स्लाइड में होगा फिर वो ऊपर वाला जो इलेक्ट्रॉन सिचुएशन का ऐसा है साइन यू शिफ्टेड टू द राइट so why you always try to show them like this because whenever you are exciting a molecule, energy doesn't really have anything. When you are moving up, the energy will diagram. You are definitely moving from the most bonding orbital to most dense. The antibody orbital, they are going to be the antibody, yeah, because of the less electron density मतलब बहुत फंडामेंटल होता है दो न्यूक्लियस के बीच में इलेक्ट्रॉन अगर ज्यादा है तो निश्चित तो अगर कम हो गया तो एंटीबॉडी कैरेक्टर्स इससे कैसे करते हैं तो रिड्यूसिबल इलेक्ट्रॉन जब इसलिए न्यूक्लियर पोजीशन में न्यूक्लियर पोजीशन ऊपर वाले देखता है potential there is from as the excited state. That potential will be excitation. Get to the very basics. So, so this is what is so nucleus is if suppose when the photon comes and it is absorbed and excitation occurs, the nucleus is here and it is the same position. The excitation occurred like this. So it is the we call it vertical excitation because the nucleus is still vibrations are very slow process as compared to electronic excitation. So the nucleus has not moved. जो vibration हो रहा था when direct movement of the nuclei and that nucleus is time to adjust itself at the time instead of photon getting when the light interacts with electrons. Okay, so this is the thing that electron is now which was at the center of the मतलब पहले जहाँ पे यहाँ पे था अब ये टर्मिनल पोजीशन पे है ऊपर वाले एक्साइटेड स्टेट के हिसाब से उस एंड इट इज एट अ डिफरेंट वाइब्रेशनल लेवल सो एक वाइब्रेशनल यहाँ पे होगा बीच में कुछ होगा ऐसे लेकिन सो इट इज getting excited so nuclei are much more massive than electrons. Electronic transitions takes place very much faster than as compared to nuclei has little time to respond. उस समय तुरंत adjust नहीं होगा. So at the time of interaction with the photon, the nuclei are treated as stationary because their movement is 1000 times slower than electrons. Electron की movement के comparison में इसका 1000 times slower. Nuclear positions. ठीक है. But after some time, because of the changed electronic environment, electron के पास positive charge है, उसका electron density profile around nucleus is changed, and so nucleus is again trying to readjust to attain the best possible situation, best possible. So उस case में, so there will be so because the electron density profile has changed, slowly it will adjust, and with a new equilibrium that you are seeing here. उस मीन के आसपास तो मीन पोजीशन में वाइब्रेशन करना वो चेंज होता है पहले आपका ये मीन था इक्विलिब्रियम, अब वो इक्विलिब्रियम पोजीशन यहाँ पे है. So now it will vibrate after the excitation. Now nuclei will readjust and a new mean, they will vibrate about a new mean position. Okay? So this is what it says. So electronic ground state, electronic excited state, and it is at the turning point of the vibrational motion. While initially यहाँ पे you started with a vibrational motion at the center, at the mid of the vibrational motion, which was the mean position. You ended up at the terminal point here, turning point of the stationary of the excite vibration, this vibrational level. So because of the changed new force field, because of new electron density has changed, rapidly changes, the nuclei start to respond and the vibration is adjusted accordingly. The with respect to the new equilibrium position. So it is so the stationary so the last point देखो क्या कहा गया, stationary equilibrium separation. मतलब ये अगर उस फ्रीज कर दो फ्रेम को कुछ देर के लिए, तो ये स्टेशनरी, यहाँ पे ये मीन पोजीशन था, वो अभी यहाँ पे टर्मिनल पोजीशन. स्टेशनरी इक्विलिब्रियम सेपरेशन ऑफ द न्यूक्लियाई इन द इनिशियल स्टेट था यहाँ पे, now becomes a stationary turning point at the for the new electronic state. नए इलेक्ट्रॉनिक स्टेट में वो टर्निंग पॉइंट बन जाता है. अगर इस पॉइंट से हम स्टार्ट करते इमेजिन करें तो ऐसी सिचुएशन इमर्ज कर रही है. So, so most intense vibronic. So now the possibility is the electron could be here, can be here, can be here. The actual position of the nuclei, electron position नहीं कह रहा हूँ, nuclear separation है ना. The nuclear position can, because it is undergoing vibration, it may change. So possibility और भी अलग अलग वाइब्रेशन लेवल पे जाने की है, लेकिन अब वो हम देखेंगे कि वो कैसे. लेकिन अगर हम ये वाला कंसिडर करें तो यहाँ पे विल सी मोर इनटू दैट, ट्राई टू अंडरस्टैंड. So transition to this vibrational state will occur, transition to other vibrational level will also occur, but that will be of lower intensity. The one that happens most intense जो transition होगा, vibrational transition, that will be the most intense will be when the ground vibration state to the vertical above it. So directly जो यहाँ देख रहे हैं, so it can be understood better way if you understand the quantum mechanical description of vibration. You understand the profile of the ground vibration state में कैसा wave function का profile है, इसको ठीक से एनालाइज करते हैं तो आपको समझ में आता है और अच्छे से समझ में आएगा कि suppose this is the electronic excited state. So you have possibilities. आपको याद होगा कि इनिशियली हम डिस्कशन कर रहे थे हार्मोनिक ऑसिलेटर का डायग्राम बनेगा, वेव फंक्शन मतलब वेव के अंदर खत्म नहीं होता. हाँ, जैसे यहाँ पे ड्रॉप जाएगा ना. So when you are writing this, so this is your vibration for psi. Vibrational for vibration, if you write vibrational wave function initial, and this is psi f, psi v comma f final. Looking at the vibrational wave function, आपको क्या लगता है? So जब आप ये लिखते हैं, so excitation, so you have dipole moment operator, transition dipole, will be given by this psi, कुछ ऐसा होगा म्यू ऑपरेटर. So it is the overlap of this, जो जिस पॉइंट पे वो नीचे वाला है तो वहां पे जो प्रोफाइल बन रहा है उसके साथ कितना अच्छा मैचिंग प्रोफाइल को कलर का होगा, that will be maximum value. Okay. So when we analyze this point, we the one with the star labeled as star, जो भी वाइब्रेशन लेवल है, यहाँ का प्रोफाइल देखिए बिल्कुल इसके जैसा मैच कर रहा है. So psi f psi I, so if there is good overlap of final and initial, then the transition dipole will be much higher value. Dipole का वैल्यू ज़्यादा होगा, direction को होगा, absorption कम. So you will see that this is high intensity of the. So this is an important principle that vibration वाले की कहाँ सबसे ज़्यादा intensity है. So और there are several vibrations. So जहाँ पे वो पीक है और किसी का जीरो है वहाँ पे उसके साथ प्रोवाइड करेगा तो ट्रांजिशन टाइप ऑफ जीरो है. If the ground state you are having this kind of profile, maximum amplitude, and then you multiply it with something which is having zero at the same point, which might be case in some of these. तो वहाँ पे तो आपको फिर प्रॉब्लम हो जाएगी ना. सो अगर आप ग्राउंड स्टेट वाले कुछ लेके चलते हैं तो वो उसका यहाँ कहीं पे होता, जैसे इसका जो ग्राउंड v इक्वल टू 0 होगा वो कहीं यहाँ पे होगा और इसका ठीक है ऐसा होगा. तो यहाँ पे तो ये बिल्कुल ही नहीं हो सकता क्योंकि यहाँ पे इसका ऑलमोस्ट 0 जैसा जाएगा. So, in a similar fashion, you look for the v equal to 0, 1, 2, 3. This one will be also defined for this position. So these will fall about the level. So there will be significant intensity at some other points, but maximum intensity will be observed where there is perfect matching with the amplitude or the wave profile. Profile of the wave function of the vibrational wave function. Okay. So that is what is stated here. Upper vibrational state that most closely resembles the vibrational, मतलब लगभग लगभग अब ऊपर वाला वेव फंक्शन नीचे वाले ग्राउंड वेव फंक्शन के जैसा मिलता जुलता दिखेगा. उस पर्टिकुलर पॉइंट पे जो लाइन ऑफ स्टेट लाइन ऊपर की तरफ that is that will give you the maximum value of absorption. Okay. ठीक है, because your transition dipole is much higher magnitude. So interacting system is. So that is the quantum mechanical explanation that we have for this kind of thing. So greatest overlap integral. So this is what we define by overlap integral. Overlap integral इसी को कहते हैं. Integral having the operator in the middle and the wave functions of final and initial states. ठीक है. So here we are looking at in electronic transitions वहाँ पे रोटेशनल वाइब्रेशन दोनों को एक साथ देख रहे थे. यहाँ पे वाइब्रेशन और इलेक्ट्रॉन दोनों वेव फंक्शन को एक साथ आप लेके चलो. ठीक है. कल का क्या जस्ट